Quarks are among the most fundamental building blocks of matter, yet their existence follows a uniquely structured logic. Unlike electrons, which can exist independently, quarks are never found in isolation. They are bound by the strong color force, the strongest force in nature, forming protons, neutrons, and other particles essential to the universe's stability. But their uniqueness goes beyond their physical properties. It lies in the deep triadic structure that governs their behavior. At every level, quarks adhere to triadic constraints. They possess three distinct color charges, must combine in triplets to form stable particles, and interact through processes that naturally follow triadic logic. This is not a coincidence but a reflection of a deeper principle of order in the universe. By analyzing quarks through the lens of triadic logic, we uncover fundamental patterns that dictate their existence, interactions, and transformations. Patterns that hint at an underlying structure within the very fabric of reality. At the heart of quark theory lies an inescapable triadic structure. The most striking example is color charge, a quantum property that comes in three distinct types: red, green, and blue. Unlike electric charge, which operates in a binary positive-negative system, color charge requires a balance of three components to form a stable, neutral system. Just as red, green, and blue light combine to form white, a quark system must contain all three color charges to remain stable. This is not just a physical constraint, but a triadic necessity. No single quark can exist alone because color neutrality demands interdependence. The triadic nature of quarks extends beyond color charge to flavor, the property that distinguishes the six types of quarks: up, down, strange, charm, top, and bottom. While electrons have only one fundamental identity, quarks exist as part of a structured hierarchy in which their mass, charge, and interactions follow ordered patterns. The most common quarks, up and down, form the foundation of protons and neutrons, which themselves rely on a three-quark configuration for stability. This necessity of triplet formation, seen in baryons like protons, which consist of two up quarks and one down quark, and neutrons, which consist of two down quarks and one up quark, arises directly from quantum chromodynamics, or QCD. The strong force carried by gluons enforces color-charge balance, making isolated quarks impossible. Quark systems do not just prefer to exist in groups of three, they must do so, or they cannot exist at all. Quarks do not just passively exist within triadic structures. Their interactions also follow distinct triadic logic in three fundamental ways: triadic coexistence, causal decay, and non-linear feedback. Because of how color charge functions, quarks must always exist in combinations that sum to a neutral state. A proton, for example, consists of two up quarks and one down quark, each carrying a different color charge. This balance is dynamically reinforced through constant gluon exchange, ensuring that the color state remains stable. This self-reinforcing process mirrors a feedback loop, where the presence of one quark necessitates the presence of others. The process of quark decay follows a strict causal structure. A top quark will always decay into a bottom quark, which then transforms into a strange or down quark. This predictable, ordered sequence is an example of causal triadic logic, where each transformation is logically dependent on the previous one. The decay cannot skip a step. If one transformation does not occur, the entire chain collapses. Unlike most force carriers, gluons themselves carry color charge, meaning they can interact with each other. This leads to recursive, non-linear feedback loops, where the strong force becomes more intense rather than dissipating. This is why quarks cannot be isolated. As soon as an attempt is made to separate them, the force grows strong enough to create new quark-antiquark pairs, reinforcing the triadic structure rather than breaking it. Unlike most particles in physics, quarks do not exist as isolated entities or simple binary pairs. Instead, their very existence demands triadic relationships, whether in color charge, confinement, or decay sequences. At every level, their behavior follows strict logical dependencies, forming the foundation for all stable matter in the universe. This triadic structure is not an accident. It is a fundamental pattern embedded within the deepest laws of physics, one that extends beyond quarks into the very nature of the cosmos. The universe does not merely allow triadic order, it requires it. By studying quarks through the lens of triadic logic, we gain not only a deeper understanding of particle physics, but also a profound insight into the universal structures that shape reality itself.